What if I told you that Earth was never alone, that 4.5 billion years ago, a world almost identical to ours formed in the exact same orbit, traveled the exact same path around the Sun, and then simply disappeared? No explosion. No debris trail. Just gone. And the terrifying part? Scientists now believe that planet didn't vanish at all. It became part of us. I'm going to say the name of this planet right now, and I want to warn you in advance: Theia. Theia. And yes, I've been saying that wrong for apparently 3 years, so we're starting strong here. By the end of this documentary, you will never look at the moon the same way again. And I mean that literally, not as a figure of speech. Because what we're going to uncover in the next 60 minutes is not a story about something that happened out there, to some other world, in some abstract ancient past. This is a story about you. About the ground beneath your feet. About the water inside your cells. About the sky above your head every single night. Something happened here. Something was erased. And we're going to find out exactly what. We're going to step back 4.5 billion years together, and what we find is going to reshape everything you thought you knew about how our world came to be. Let's start where all origin stories start, with absolute chaos. The solar system we live in today looks orderly. The Sun sits at the center. 8 planets orbit in neat, roughly circular paths. Asteroids stay in their belt. Everything has a place. But that orderliness is a survivor's illusion, the calm surface of a system that spent its first several hundred million years in something closer to a demolition derby than a construction project. 4.6 billion years ago, there was no solar system. There was a spinning cloud of gas, dust, and ice, a protoplanetary disk stretching across a volume of space you cannot meaningfully imagine, orbiting a newborn star that had just ignited its hydrogen fusion engine for the first time. Within this disk, gravity was already playing favorites. Tiny grains of dust stuck together into pebbles. Pebbles stuck together into boulders. Boulders accumulated into planetesimals, objects ranging from the size of a mountain to the size of a small country, and the planetesimals, under the relentless pull of gravity, were building something bigger. This process is called accretion. And it was not, to put it gently, a gentle process. The average collision speed between planetesimals in the early inner solar system reached somewhere between 5 and 10 kilometers per second. That's fast enough to vaporize rock on contact. We're not talking about things bumping softly together and merging, we're talking about high-velocity impacts that released energy comparable to nuclear detonations, happening thousands of times per day, across the entire disk, for hundreds of millions of years. Out of this violence, a few bodies grew large enough to dominate their orbital neighborhoods. Scientists estimate there were dozens of Mars-sized protoplanets competing for orbital real estate in the early inner solar system. Dozens. And the orbital real estate was limited. Physics was going to force a reckoning. Now, here's the piece of this I need you to sit with for a moment, because it's the foundation of everything else in this documentary. Every planet, as it grows, shapes the gravitational landscape around its orbit. And within that landscape, there are special locations, stable gravitational pockets, where smaller objects can accumulate without immediately being swept up or ejected. These are called Lagrange points. Specifically, the L4 and L5 points, which sit roughly 60 degrees ahead of and behind a planet in its orbital path. These aren't theoretical constructs. We can see them operating right now. The James Webb Space Telescope, humanity's most powerful eye in the cosmos, is parked at Earth's L2 Lagrange point as we speak. The same gravitational mechanic that holds Webb in place is the one that, 4.5 billion years ago, may have been cradling Earth's twin. I genuinely don't think that's a coincidence so much as the universe having an understated sense of irony. What was Proto-Earth like at this point? Scientists sometimes call it Gaia, the earlier, incomplete version of our world before the event that defined it. It was roughly 90% of today's Earth's mass. Its surface was a global magma ocean, temperatures exceeding 1200 degrees Celsius, no atmosphere as we understand it, no oceans, no crust stable enough to stand on. A molten, roiling sphere of mineral hell. And sitting in Earth's orbital blind spot, growing quietly, accumulating mass, following the same path around the sun year after year for tens of millions of years, something was taking shape. A companion. A twin. Something that would be Earth's constant, silent partner for longer than our minds can properly grasp. Its name, when scientists finally gave it one, was Theia. And here's the detail that makes Theia unlike anything else in solar system history: it didn't just share Earth's neighborhood. According to the dominant model of how the Moon formed, Theia may have shared Earth's exact orbital path, meaning for millions upon millions of years, these two worlds were essentially the same planet, split in two, circling the Sun in perfect gravitational lockstep. They rose and fell with the same rhythm. They traced the same arc through space. They were bound together by physics in a way that felt permanent. Until, with the slow inevitability of mathematics, it wasn't. So who was Theia, exactly? Because I think this is where the story gets genuinely strange, and genuinely moving, once you understand the full picture. The name itself comes from Greek mythology. Theia was the Titan goddess who was the mother of Selene, goddess of the moon, and Helios, god of the sun. The scientists who named this lost world were being poetic, and they earned the right to be. Because the naming turned out to be almost prophetically accurate in ways nobody anticipated when the hypothesis was first seriously proposed. When we talk about Theia's size, there's an honest debate in the literature that I want to be upfront about. The most widely cited models place Theia at roughly 1/10 of Earth's mass, Mars-sized, which is already a substantial world. But research published in 2021 suggests it may have been considerably larger, potentially half of Earth's mass. If that's true, Theia wasn't a small body at all. It was a sub-Earth, a world in its own right, with a layered internal structure including an iron core and silicate mantle, with active volcanism, with its own geological history playing out in parallel to Earth's for tens of millions of years. Think about that. Not a rock. Not an asteroid. A world. And here's the detail that honestly unsettled me more than any other when I was digging through the research. The chemical evidence from Apollo moon samples shows that the oxygen isotope ratios in lunar rocks are nearly identical to Earth rocks. Nearly identical. And this is a problem, a beautiful, revealing problem. Planets that form at different distances from the Sun have different isotopic fingerprints. Venus is different from Earth. Mars is different from Earth. The asteroid belt is different from both. But Theia and Earth match. They match because Theia formed in the same region of the solar system as Earth, which means they were built from the same ingredient list, cooked in the same cosmic kitchen, at the same orbital address. They were twins in the most literal chemical sense. And the evidence for Theia goes deeper than moon rocks. In 2021, a research team led by Qian Yuan published a study in Nature Geoscience identifying two massive structures in Earth's deep mantle, continent-sized blobs sitting approximately 2,900 kilometers beneath our feet, one beneath Africa and one beneath the Pacific Ocean. These structures, called large low-shear velocity provinces, are denser and chemically distinct from the surrounding mantle. They don't fit. They're anomalous. And the most compelling explanation for their presence is that they are remnants of Theia's mantle, material that sank during the giant impact and never fully mixed into Earth's interior in the 4.5 billion years since. I want to pause here because this is the part that wrecks me every time I sit with it. We have a piece of another planet inside us. Not metaphorically. Geologically. The ground you're standing on, at its very deepest detectable layer, at a depth we can measure with seismic waves but will never physically reach, might be alien. That's not speculation dressed up as science. That's what peer-reviewed research in 2021 is telling us. Okay. Moving on. So Theia was real. It was large. It was chemically indistinguishable from early Earth in many key respects. And for millions of years, it existed in a gravitational equilibrium that should, by any naive reading of orbital mechanics, have lasted indefinitely. So what went wrong? What went wrong is that the equilibrium was never as stable as it looked. And the deeper you understand the physics, the more you realize that Theia's destruction wasn't random bad luck. It was structurally inevitable, written into the laws of orbital mechanics from the moment Theia first formed. Here's the mechanism. Lagrange point stability comes with a condition attached. The mass ratio between the primary body and its Lagrange companion must stay below a critical threshold. As long as Theia remained small relative to Earth, the gravitational balance held. But Theia was growing. Everything in the early solar system was still accreting, still gathering mass from the disk. And as Theia grew larger, the margin of stability shrank. Eventually, given enough time and enough small perturbations, the equilibrium was going to break. The perturbations came from Jupiter. Jupiter's gravitational influence on the inner solar system is not a background hum, it's a dominant force that has shaped everything inside Mars's orbit. And during Jupiter's early orbital migration, a process documented in what planetary scientists call the Grand Tack hypothesis, Jupiter moved significantly inward and then outward again, sending gravitational shockwaves through the inner solar system in the process. Those shockwaves nudged bodies off stable paths. They stirred up the asteroid belt. They altered the orbital characteristics of every protoplanet in the inner solar system. And for Theia, parked at its Lagrange point with an increasingly tenuous hold on stability, Jupiter's perturbations were the final variable that tipped the balance. Once destabilized, Theia's orbit became increasingly eccentric. Imagine two ice skaters holding hands and spinning together. While both pull with equal force, the system is stable, beautiful, controlled. The moment one skater starts to drift, the whole thing goes chaotic. Theia was the skater who started to drift, and once the drift began, it could not be stopped. Before the final collision, Theia likely made multiple close approaches to Earth over thousands or millions of years. Each near miss would have generated enormous tidal forces between the two bodies, stretching their surfaces, triggering volcanic eruptions on both worlds, distorting their shapes. From the surface of early Earth, during one of these close approaches, Theia would have dominated the sky. An entire other planet, close enough that its geological features would be visible, creeping slowly across the heavens, drawing Earth's magma ocean into enormous tidal bulges. And then receding. And then returning, closer. And then receding again. Each pass bringing the two worlds fractionally nearer to their appointment. Research by Jacobson and Morbidelli, published in 2014, used n-body simulations, computational models tracking the gravitational interactions of hundreds of bodies simultaneously, to show that the giant impact was almost certainly the last major accretionary event for Earth. Theia's collision was Earth's finishing blow. The impact delivered the final mass that completed our world. Without Theia, Earth stays at 90% finished, forever. A planet that never quite became itself. The laws of orbital mechanics practically scheduled this collision from the start. And somehow, knowing it was never a matter of if but only when, makes the whole thing feel less like a catastrophe and more like a plan nobody wrote. Approximately 4.45 billion years ago, give or take a few million years, the appointment arrived. The giant impact. This is the moment everything in Earth's history turns on. And I want to be precise about the details here, because the precision is what makes it comprehensible at scale. First, the geometry. Theia didn't hit Earth head-on. The current best models, built on decades of computational work including Robin Canup's landmark 2004 simulations at the Southwest Research Institute, suggest the impact angle was roughly 45 degrees, an oblique, grazing collision rather than a direct strike. This matters enormously, because a head-on collision would have produced a very different outcome, likely a merged planet with no debris disk, no moon, no story. The specific angle of Theia's arrival was one of the conditions that made everything afterward possible. Second, the speed. Because Theia was co-orbital, approaching from roughly the same direction Earth was traveling, rather than crossing Earth's path at a steep angle, the relative velocity at impact was slower than typical asteroid impacts. Approximately 4 to 5 kilometers per second. Still catastrophic, but slow enough for the collision to be what scientists call a merger, rather than a pure disintegration. Now, what happened in the hours that followed? At the moment of first contact, Theia's leading edge strikes Proto-Earth's mantle. The kinetic energy of an object with potentially half Earth's mass moving at 4 kilometers per second converts to heat with a speed that has no human analogy. Rock vaporizes. A shock wave propagates through both bodies at the speed of sound in compressed silicate, roughly 8 kilometers per second, passing through the entire volume of both planets within minutes. Within the first 6 hours, both worlds begin to deform catastrophically. Theia's iron core, denser than the surrounding silicate rock, punches through the chaos toward Earth's core like a bullet through water. The mantles of both worlds, the thick rocky layers between core and crust, are splashed outward in a spray of vaporized and semi-molten material that towers thousands of kilometers above what used to be a surface. The energy released across this event is approximately 100 million times the energy of the asteroid impact that ended the dinosaurs. The Chicxulub impactor gets all the cultural attention. The giant impact makes it look like a pebble. The temperature at the impact point reaches 10,000 degrees Celsius, hotter than the visible surface of the Sun. Within 24 hours, the worst is structurally over. The combined mass, Earth plus most of Theia's material, has begun to coalesce into a new, larger body. A rotating disk of debris surrounds it, vaporized rock, partially molten chunks, superheated plasma, the shredded remnants of two worlds mixed at temperatures where the distinction between them has become chemically meaningless. This disk is hot, dense, and orbiting close in. And within it, gravity is already doing what gravity always does, pulling things together. The moon is being born. I've read somewhere around 30 papers on the giant impact while making this documentary, and I genuinely still can't fully process the scale of what we're describing. We're talking about an event that melted the entire surface of a planet. Everything. The nascent crust, the mineral deposits, the proto-atmosphere. All of it vaporized. And then, over millions of years, it cooled. It healed. New crust formed. Oceans arrived. Life happened. And 4.4 billion years later, here we are, standing on the scar, wondering what it looked like. I find that simultaneously horrifying and one of the most miraculous things I've ever learned. One more detail I have to flag here before we move on, because I always mix these numbers up and I want to be precise. The energy figure I cited, 100 million times the kpg impact, refers to the total energy budget of the giant impact event, not the Chicxulub crater energy specifically. There's a meaningful difference in how those figures are calculated, and it matters for understanding the scale correctly. In less than a single day, 2 planets became one. Theia was gone, absorbed, vaporized, merged beyond any hope of chemical separation. And from the debris rain left behind, something new was coalescing. Something that would change Earth's trajectory in ways we're only now beginning to fully understand. The Moon. We talk about the Moon as if we've understood it for centuries. And in some ways we have, its phases, its tides, its distance. But the deeper story of what the Moon actually is has only come into focus in the last 50 years. And that story is stranger and more significant than most people realize. The giant impact hypothesis, the scientific model that the Moon formed from the debris of a collision between proto-Earth and Theia, was first formally proposed in 1975 by 2 independent research groups, Hartmann and Davis on one side, Cameron and Ward on the other. It was initially controversial. It seemed almost too dramatic, too specific, too convenient. Over the following decades, however, the evidence accumulated to a point where it became the dominant and now near universally accepted explanation for the Moon's origin. And the evidence is compelling in a way that deserves careful attention. Start with angular momentum. The Earth-Moon system has an unusually high total angular momentum, more rotational energy than you'd expect from a planet that simply formed and acquired a moon through capture or co-formation. The mathematics of that angular momentum matches almost perfectly with the expected outcome of a Mars to sub-Earth-sized oblique impact. No competing model, not co-formation, not capture, not fission, reproduces that number as cleanly. Then look at the Moon's composition. The Moon has a much smaller iron core than Earth, only about 20% of its radius, compared to roughly 50% for Earth. This is exactly what you'd predict if Theia's iron core merged with Earth's core during the collision, leaving the debris disk, which became the Moon, depleted in iron and enriched in lighter silicate material. Then look at what the Moon doesn't have. Volatile elements, water, sodium, potassium, and other compounds that evaporate at high temperatures, are severely depleted in lunar rocks compared to Earth. This is consistent with the extreme temperatures generated during the impact, stripping those volatiles away from the debris before the Moon assembled. And then, looping back to what I mentioned earlier, the deep mantle blobs. The 2 continent-sized LLSVPs beneath Africa and the Pacific, sitting at the boundary between Earth's mantle and core, never fully mixed in 4.5 billion years. Yuan and colleagues' 2021 analysis suggests these structures are denser and compositionally distinct in ways that match what you'd expect from Theia's mantle material that sank and settled. Not Earth's mantle, processed and homogenized over geological time. A foreign body, preserved in the deepest accessible layer of our world, unchanged since the day of impact. Theia didn't vanish. It's underneath you right now. The Moon formed extraordinarily quickly after the impact, within decades to centuries by some estimates, which is essentially instantaneous by geological standards. And the early Moon was nothing like the distant silver disk we know. It formed at a distance of perhaps 10 to 20 times closer to Earth than its current orbital distance of 384,000 kilometers. At that proximity, the Moon would have appeared 10 to 20 times larger in the sky, a vast, glowing, partially molten world dominating Earth's horizon, close enough that its tidal forces raised ocean bulges kilometers high once liquid water eventually arrived on Earth's surface. The Earth's day, in the period shortly after the impact, lasted approximately 5 to 6 hours. A full rotation every few hours, under the watch of an enormous moon pulling at the surface. Over billions of years, through a process called tidal braking, where the moon's gravity gradually transfers rotational energy out of Earth's spin, the day lengthened to its current 24 hours, and the moon receded to its current distance. We can measure that recession directly. Apollo astronauts left laser reflectors on the lunar surface, and we bounce laser beams off them to this day. The moon is currently moving away from Earth at approximately 3.8 centimeters per year. Run that number backward through time, and it confirms the timeline of the giant impact with remarkable precision. But here is the piece of the moon's story that I think deserves the most attention, the piece that connects Theia's death to your existence in the most direct possible way. Without the moon, Earth's axial tilt would not be stable. Earth's spin axis is currently tilted at about 23.5 degrees relative to its orbital plane, and it remains within a relatively narrow range of variation because the moon's gravitational influence acts as a stabilizer. Without the moon, simulations show that Earth's axial tilt could swing chaotically between 0 degrees and 85 degrees over geological timescales. At 85 degrees of tilt, Earth would be rotating nearly on its side, the poles pointing roughly at the sun for half the year, plunged into total darkness for the other half. The climate would be unrecognizable. Seasons as we know them would not exist. The stable, cyclical environmental conditions that allowed complex life to evolve over hundreds of millions of years, gone. Here's the thought that genuinely keeps me up at night: without Theia, there is no stable Earth. Without Theia, the axial tilt goes haywire, the climate swings to extremes that may have been incompatible with the slow, patient process of biological evolution. Without Theia, the tidal pools that many biologists believe were among the cradles of early life, those shallow, chemistry-rich zones where the ocean meets the land, churned by twice-daily tides, never exist with the regularity and vigor needed. The specific conditions that allowed the first self-replicating molecules to form, disrupted from the start. You and I, not gone from a later catastrophe, gone from the very beginning. Theia didn't just die. Theia's death was the precondition for life. I know that's not how physics works, in the sense that physics doesn't have intentions. But it's extraordinarily difficult not to feel it that way. Anyway, the science. Theia is not the only world that was erased. And this is where the story expands from a single planetary biography into something that forces us to reckon with what kind of solar system we actually live in. Here's a fact that should bother you more than it probably does. When astronomers look at other planetary systems, particularly those around sun-like stars, they find them full of what we call super-Earths, planets larger than Earth but smaller than Neptune, orbiting relatively close to their host stars. These are the most common type of planet found by the Kepler and TESS space telescopes. They're everywhere. In system after system after system. And our solar system, conspicuously, does not have any. The inner solar system, the region from the Sun out to Jupiter, contains only Venus, Earth, and Mars, all of them smaller than the average planet we'd expect based on statistics from other systems. The mass that should be there, based on what we see elsewhere, is missing. It went somewhere. The most compelling explanation currently under study is what researchers including Matt Clement have proposed. Our solar system once contained one or more super-Earth-class planets in the inner system, and they were destroyed or ejected during Jupiter's early inward migration, the Grand Tack, before the current terrestrial planets finished forming. The asteroid belt, which today contains only about 4% of the Moon's total mass, was once a far richer reservoir of material. Jupiter's gravitational sculpting hollowed it out, and the same process may have eliminated entire worlds. The nice model of solar system evolution, proposed by Tsiganis and colleagues in 2005, describes a period of orbital instability among the outer planets that ejected several smaller bodies completely from the solar system. Not into the asteroid belt. Not into distant cold storage orbits. Out. Gone. Traveling through interstellar space right now, if they still exist as coherent bodies at all. Compare our solar system to TRAPPIST-1, 7 Earth-sized planets orbiting a single star in closely packed orbits. This is the kind of inner system architecture our solar system might have resembled before Jupiter intervened. 7 worlds. We have 3. The other 4, or their equivalent mass, was processed away. And then there's the Planet 9 question. The clustering of trans-Neptunian objects, small bodies in the far outer solar system, shows a gravitational pattern that some researchers interpret as evidence for an undiscovered planet of 5 to 10 Earth masses, orbiting at extreme distances, possibly captured from another star system or possibly an ejected body from the inner solar system that didn't quite achieve escape velocity. The data is contested, the interpretation is uncertain, but the gravitational anomaly is real. The solar system we inhabit is not a pristine formation. It's a survivor's landscape, shaped by loss, by ejection, by destruction, by the grinding violence of 4 billion years of gravitational dynamics. The worlds that exist today are the ones that happen to be in the right place at the right time with the right mass. The ones that weren't, aren't here to tell their stories. And in that context, Theia's fate looks less like an accident and more like standard procedure. If Theia is Earth's lost twin from the ancient past, Venus is something different. It's Earth's surviving mirror, present and accounted for, sitting just inside our orbital path, and it is one of the most unsettling objects in the solar system once you understand what it represents. By the numbers, Venus and Earth are nearly identical twins. 95% of Earth's diameter. 81% of Earth's mass. Similar bulk density. Similar internal structure. If you built Earth and Venus side by side from scratch in a laboratory, using the same materials, they would be nearly indistinguishable. And yet Venus is, without exaggeration, a hell's cape. Surface temperature averaging 465 degrees Celsius, hot enough to melt lead. Atmospheric pressure 92 times Earth's, equivalent to the pressure you'd experience 900 meters underwater. An atmosphere of carbon dioxide so thick it traps heat with catastrophic efficiency. Clouds of sulfuric acid. No water. No life. Nothing. Venus also rotates backwards relative to most planets, retrograde rotation, with an extraordinarily slow spin that means a Venusian day is longer than a Venusian year. This combination of retrograde rotation and extreme slowness is deeply anomalous, and the most credible explanation researchers have proposed, in work spanning from 2019 to 2023, is that Venus experienced its own giant impact early in its history, one that reversed and drastically slowed its rotation. Venus has a Theia story. It just ended differently. More troubling still, evidence accumulated over recent decades suggests Venus may have been habitable for up to 3 billion years. Possibly even longer. Climate models by Michael Way and others suggest that ancient Venus, rotating slightly faster and with different cloud dynamics than today, could have maintained surface temperatures compatible with liquid water through a very long portion of solar system history. 3 billion years is longer than Earth has had complex multicellular life. That is more than enough time, in principle, for life to develop and thrive. And then, approximately 700 million years ago, according to current geological dating of Venus's resurfaced terrain, something catastrophic happened. A runaway greenhouse effect, triggered by outgassing from extensive volcanism, tipped Venus's climate into a feedback loop it could not escape. The oceans evaporated. The water vapor drove more warming. The heat drove more volcanism. The carbon dioxide accumulated to crushing density. Venus became what it is today. NASA's Da Vinci Plus and Veritas missions, both approved in 2021, are the first dedicated Venus missions in decades. They are specifically designed to answer the habitability question, to look for chemical evidence of ancient oceans, to map the geology, to determine whether Venus's surface preserves any record of a wetter, calmer past. That data doesn't exist yet. But the question is being asked seriously, in peer-reviewed science, funded by the world's most prominent space agency. And then there's the phosphine episode. In 2020, a research team announced the detection of phosphine, a gas with no known abiotic production mechanism in planetary atmospheres, in Venus's cloud layer. The claim was immediately controversial, the methodology questioned, the detection subsequently revised downward. The scientific status of that detection remains unsettled. But the possibility it opened, that microbial life might persist today in Venus's temperate cloud layer, at altitudes where temperatures and pressures are surprisingly Earth-like, potentially descendants of organisms that survived the runaway greenhouse by adapting to atmospheric conditions, has not been closed. I think Venus gets unfairly sidelined in popular science. We talk about Mars constantly. Mars this, Mars that, maybe life on Mars, maybe we move to Mars. Venus is right there. Same size as Earth. Possibly had oceans for billions of years. Possibly had life. And now it's a furnace. I think we avoid Venus because it's not, maybe there's life, it's, maybe there was life, and here's what happened to it. Venus is the warning label on the bottle that we'd rather not read. So we've watched a twin world form, live quietly for millions of years, destabilize, and collide catastrophically with Earth. We've watched the moon emerge from the wreckage. We've examined the evidence that pieces of Theia are still with us, in the mantle and in the sky. And we've seen that Theia's story is part of a larger pattern, a solar system that has been erasing planets throughout its history. But here is the question I've been holding back, because I think it's the most important one in this entire documentary: what did the collision actually give us, beyond the moon? Because it turns out the giant impact was not purely destructive. The collision, and the period of bombardment it helped trigger, may have been the delivery mechanism for the very ingredients that made life on Earth chemically possible. Consider the water problem. Earth's accretion zone, the region of the solar system where proto-Earth formed, sits inside the snow line, the distance from the sun at which water ice can exist in solid form. Inside the snow line, the solar system should have been relatively dry. The temperatures were too high for ice to survive in the protoplanetary disk. The material Earth accreted from should have been water poor. Yet Earth has water covering 71% of its surface. Approximately 1.3 billion cubic kilometers of liquid water on and in the planet. Where did it all come from? Comets were the first proposed answer. Comets carry water ice. But the deuterium to hydrogen ratio in cometary water, a precise chemical fingerprint that records where in the solar system the water formed, doesn't match Earth's oceans. Comets are ruled out as the primary source. The current leading candidate is carbonaceous asteroids, the C-type bodies from the outer asteroid belt, water-bearing rocks whose isotopic ratios match Earth's water closely. Samples returned from asteroid Ryugu by the Hayabusa 2 mission in 2020 and from asteroid Bennu by OSIRIS-RX have confirmed that these bodies carry organic molecules, amino acid precursors, and water-bearing minerals. This is the material that Earth's oceans may ultimately derive from. The giant impact connects to this because the collision caused the final major gravitational restructuring of the inner solar system. The debris, the orbital perturbations from Theia's destabilization, and the subsequent dynamical chaos set outer asteroid belt material on Earth-crossing orbits. The late heavy bombardment, a period of intense impact activity roughly 4.1 to 3.8 billion years ago, delivered the water, the carbon, the nitrogen. The building blocks of biochemistry rained down onto a cooling Earth precisely because the giant impact had reshuffled the solar system's gravitational architecture. There's also a more direct connection being actively investigated. If Theia formed at a slightly greater orbital distance than Earth, just beyond the snow line, where volatile-rich material was more abundant, then Theia itself may have carried water and carbon directly into Earth during the collision. Some of Earth's water may be Theia's water. Some of the carbon in your body may have been inside Theia before it arrived. A 2020 study by Piani and colleagues, published in Science, found that enstatite chondrites, the class of meteorite most compositionally similar to Earth's bulk makeup, contain enough hydrogen to account for Earth's entire ocean volume. This suggests that water may have been present in Earth-forming material all along, rather than being purely an external delivery. The giant impact may have mixed and redistributed that water, driving some off as vapor and preserving the rest as the deep reservoir from which the oceans ultimately emerged. And then there's the philosophical dimension, which I'm going to get into for a moment, even though I know some of you are already reaching for the skip button. The water in your body right now, the water that constitutes roughly 60% of your physical structure, has a history older than the solar system itself. It was synthesized in molecular clouds in the interstellar medium before our sun ignited. It was incorporated into the protoplanetary disk. It survived the giant impact in some form. It arrived during the bombardment. It cycled through the first oceans and through the first living organisms. It evaporated, rained down, was metabolized and released and metabolized again across 4 billion years of biological history. And now it is in you. Every glass of water you have ever drunk is a direct physical connection to the earliest moment of this solar system's existence. I think that's worth holding for more than a moment. So we arrive at the question that the entire architecture of this story has been building toward: if the conditions that produced Earth, the giant impact at the right angle, the right speed, the right mass, delivering the right chemistry at the right time, were so precisely calibrated, how often does this happen elsewhere? And what does the answer tell us about why we haven't heard from anyone? This is the Fermi paradox dimension of Theia's story, and it's where planetary science meets astrobiology in a way that I find both electrifying and sobering. The rare Earth hypothesis, articulated by Peter Ward and Joe Brownlee in their 2000 book, argues that complex life, multicellular, intelligent, technologically capable life, requires an extraordinary coincidence of factors that may be vanishingly rare in the universe. The right size star, the right orbital distance, a large stabilizing moon, active plate tectonics, a planetary magnetic field strong enough to deflect solar radiation, the right atmospheric chemistry, a Jupiter-like outer planet intercepting comets and asteroids before they reach the inner system too frequently. Trace every one of those requirements backward, and they all lead, in one way or another, to the giant impact. The moon's stabilizing effect on Earth's axial tilt, Theia's legacy. The Earth's iron core generating the magnetic field, partially the result of Theia's core merging with Earth's and delivering the final mass to sustain a dynamo. The delivery of volatile elements that enabled plate tectonics and biological chemistry, potentially triggered by the dynamical reorganization of the giant impact. The moon we have is anomalous. Among the 4 terrestrial planets in our solar system, only Earth has a large moon. Mars has Phobos and Deimos, tiny, captured asteroids, geologically negligible. Venus has nothing. Mercury has nothing. Earth is the exception, not the rule. If the moon-forming impact required a specific combination of angle, velocity, mass ratio, and timing, and current models suggest all of these parameters mattered, then the probability of replicating our outcome elsewhere may be quite low. Some statistical analyses suggest fewer than 1% of Earth-sized planets in habitable zones will have gone through a comparable impact with a comparable result. The universe may be full of terrestrial planets that had giant impacts but produced no moon, or produced a moon too small to stabilize their axial tilt, or suffered impacts that were too energetic and simply destroyed both bodies entirely. The Fermi paradox asks, if the universe is so large and so old, why is space quiet? Why haven't we detected radio signals from other civilizations? Why haven't we been visited? One answer, not the only answer, but a compelling one, is that the chain of events leading from planetary formation to complex life is so improbable at each step that civilization-producing worlds are extraordinarily sparse in the galaxy. Perhaps we are not typical. Perhaps we are a statistical accident of breathtaking specificity. I'll be honest with you, and I mean this sincerely, this is the section of this documentary I struggled with the most in the writing. Because the rare Earth argument can feel nihilistic. Like, we're alone, nothing matters, why get out of bed? But sitting with it longer, I arrive at the opposite conclusion. If the conditions for complex life are extraordinarily rare, if we are, in some genuine sense, the universe's rare attempt at self-awareness, then that is not depressing. It is the most profound responsibility I can conceive of. We might be the only thing in this galaxy looking back at the stars and actually wondering what they are. That should terrify us, yes. And drive us, in equal and opposite measure. The search for Earth-Moon analogs in other star systems continues. Current detection technology cannot yet confirm an Earth-sized planet with a proportionally large moon around another star. Those systems are below our sensitivity threshold. But they are a stated target for the next generation of space telescopes. If we find them, it changes the Fermi calculus significantly. If we don't, that changes it too. We've come a long way from that opening question. So let me tell you where we've landed, and where Earth's story goes from here. The sun is not a static object. It brightens, slowly but measurably, at approximately 1% per 100 million years as it converts more of its hydrogen to helium and its core adjusts. In roughly 1 billion years, that additional luminosity will be sufficient to push Earth's surface temperatures high enough to begin a slow runaway greenhouse effect, the same process that claimed Venus. Complex surface life, the kind that requires liquid water and stable temperatures, may face an existential pressure on a billion-year timescale entirely independent of anything we do or don't do as a civilization. Earth's tectonic system, which regulates atmospheric CO2 through the carbon silicate cycle, will likely begin to slow and eventually cease as the planet cools further, on timescales of 1.5 to 2 billion years. Without tectonics, the carbon cycle that keeps our atmosphere breathable over geological time will fail. The Moon continues its recession, 3.8 centimeters per year, year after year. The stabilizing effect it has on Earth's axial tilt will persist for billions of years, but it is not eternal. The gravitational relationship between Earth and Moon is evolving. Everything is evolving. And in approximately 4.5 billion years, the Andromeda Galaxy will collide with the Milky Way. Galaxy collisions don't typically mean direct star-to-star impacts. Space is too vast even inside a galaxy for that to be likely. But the gravitational restructuring of a galaxy merger will alter the orbital dynamics of star systems in ways that are difficult to predict at the level of individual planets. The probability of solar system disruption from the Andromeda merger is low. It is not zero. These are billion-year timescales. The challenges humans face in the next century, climate change, biodiversity loss, resource depletion, operate on timescales that are 10 million times shorter. The cosmic risks are real, but they are slow. The human scale risks are immediate. Knowing that Earth's habitability has a geological and astronomical expiration date should not induce fatalism about the short term. If anything, knowing how specifically, how improbably, how contingently this world was constructed should make us more careful with it. Not less. The legacy of lunar science is worth naming here. Everything we know about the giant impact, about Theia, about the conditions that made Earth what it is, all of it traces back to 382 kilograms of moon rock brought back to Earth by Apollo astronauts between 1969 and 1972. 12 human beings walked on the moon. They picked up rocks. Those rocks, analyzed over the following 50 years with instruments that didn't exist when the rocks were collected, revealed the entire story we've spent this documentary telling. That is a case study in why space exploration has scientific returns that nobody could have predicted when the missions were planned. The Artemis program is in the process of returning humans to the moon for the first time since 1972. New samples, collected from regions of the lunar surface not visited by Apollo, analyzed with instruments orders of magnitude more precise than anything available in the 1970s, could answer the remaining open questions about the giant impact. Theia's exact size. The precise angle of impact. The composition of those deep mantle blobs. The relationship between the moon's volatile depletion and the timing of Earth's water delivery. The story is not finished. We are still reading it. When I started researching this documentary, I expected to find a story about a planet that died. And it is that. But it's also something I didn't anticipate, a story about how destruction can be generative. How the worst thing that ever happened to the early Earth was simultaneously the reason you and I are here, at this moment, having this conversation across whatever distance separates us. I've been sitting with that for weeks. I'm not sure I'm meant to resolve it. I suspect the discomfort is actually the point. At the start of this documentary, I told you that Earth had a twin. That it formed alongside us, traveled with us for tens of millions of years, and then vanished. Now you know the full story. It didn't vanish. It's above you tonight, in the moon. It's below you, in the deep mantle blobs beneath the Pacific and Africa. It's inside you, in the water and the carbon of your cells, delivered by the catastrophic chain of events that Theia's collision set in motion. Theia didn't disappear without a trace. It left traces everywhere, in everything. In this space documentary, we stepped back 4.5 billion years and found a planet that history forgot. We traced Theia from its quiet orbit at Earth's gravitational shoulder, through the slow-motion catastrophe of orbital destabilization, through 24 hours that reshaped everything we knew about how worlds are born. We found Theia in the moon's iron-depleted interior, in the deep mantle blobs, in Earth's oceans, and in the chemistry of life itself. And we found that the end of one world was the condition for the beginning of another, ours. Every planet in our solar system carries a story of survival or erasure. Earth's story is both. And it is still being written. If this documentary changed how you see the moon tonight, and I genuinely hope it does, then I want to ask you something small in return. Subscribe to this channel if you haven't, because I spend an unreasonable amount of time making sure every claim in these documentaries is backed by real peer-reviewed research. Every video. Every time. And leave a comment with the thing that surprised you most. I read every single one. The comments on this channel are sometimes better than the documentaries. Sometimes. Next time, we're going even further back. Before Earth. Before the solar system. To the stellar graveyard where the atoms of every living thing on this planet were forged in the death of a star that lived and died before our sun was born. The story of where we truly come from is longer and stranger than any of us imagined. I'll see you there. Looking at what's already been written, the conclusion and CTA are complete. The script has reached its natural ending point with the outro and subscribe call to action already in place. But wait, the outline shows that Part 7, Venus, Earth's other lost twin, Part 8, the gift Theia left behind, Part 9, the rarity of survival, implications for the Fermi paradox, and Part 10, what comes next, are all marked as unwritten, even though the already written section contains content that clearly covers those topics in the conclusion segment. The written ending jumps from Part 6 directly into what reads like a combined summary of Part 7 through 10, then lands in the conclusion. So the task here is to fill in what's genuinely missing, the standalone body sections for Parts 7 through 10, before that conclusion section picks up. Venus sits 38 million kilometers closer to the Sun than Earth does. That number sounds significant, and it is, but not for the reason most people assume. The difference in solar distance alone doesn't fully explain why Venus became the hellscape it is today, with surface temperatures of 460 degrees Celsius, an atmospheric pressure 90 times greater than Earth's at sea level, and clouds of sulfuric acid cycling through skies that never clear. The distance matters, but the story of Venus is really a story about tipping points, and about what Earth narrowly avoided becoming. Venus and Earth are so similar in size, density, and bulk composition that planetary scientists have called them twins for decades. They formed from the same reservoir of solar nebula material at roughly the same time. Venus is about 82% of Earth's mass. Its core is likely similar in structure. Its mantle composition is probably not dramatically different. If you lined up both planets side by side in the early solar system, before divergence set in, they would have looked nearly identical from a distance. And yet something happened to Venus. Something went irreversibly wrong. And the leading candidate for what that something was, the factor that tipped Venus from habitable to catastrophic, is the absence of a large moon. This is where the Theia story doubles back on itself in a way that genuinely stopped me mid-research, because the implications are almost too neat. Venus has no moon of any significance. No stabilizing gravitational partner. No body to maintain axial tilt within a narrow, livable range. And without that stabilization, Venus's rotational history became chaotic in ways that Earth's didn't. Venus now rotates so slowly that a Venusian day is longer than a Venusian year, 243 Earth days to complete a single rotation, compared to 225 days to orbit the Sun. It rotates backwards relative to its orbital direction, a retrograde rotation that suggests a dramatic early history, possibly including a massive impact of its own that went differently than Earth's. The runaway greenhouse effect that destroyed Venus's surface habitability, if Venus ever had liquid water, and some models suggest it may have, briefly, in its earliest history, required not just solar proximity but a destabilized climate system with no long-term corrective mechanism. Earth has several such mechanisms. The carbon-silicate cycle, regulated by plate tectonics, acts as a planetary thermostat over millions of years, drawing down atmospheric CO2 when temperatures rise and releasing it when they fall. Venus, which shows no evidence of Earth-style plate tectonics, may have lost this regulatory capacity early. Without it, a modest warming from any cause, increased solar luminosity, volcanic outgassing, a shift in albedo, could cascade into a feedback loop with no exit. And that appears to be exactly what happened. The moon's role in preventing this on Earth is underappreciated in popular science. Earth's axial tilt currently sits at 23.5 degrees, and it oscillates between roughly 22 and 24.5 degrees over a cycle of 41,000 years. That's a remarkably narrow range. Mars, which lacks a large stabilizing moon, has had its axial tilt vary between 10 and 60 degrees over millions of years, a swing so dramatic that Mars's ice caps have periodically migrated toward the equator and back. Climate chaos on that scale would have made the development of complex life extraordinarily difficult, perhaps impossible, on Earth. The moon keeps us stable. Theia gave us the moon. The chain of causation is direct. So when we look at Venus and ask what Earth dodged, part of the answer is a giant impact that either didn't happen or happened wrong. A world that formed without a stabilizing partner. A planet that had no Theia, or whose Theia arrived at the wrong angle, the wrong speed, and left nothing useful behind. The difference between Earth and Venus, between life and a pressure cooker hell, may come down to the precise geometry of a collision that happened 4.5 billion years ago. A few degrees of deflection in Theia's trajectory. A slightly different mass ratio. A different impact velocity. And we might be Venus. That's not dramatic framing for effect. That's the actual scientific inference. And it should sit with you for a moment. Let's talk about what Theia actually left behind, because the list is longer and stranger than the moon alone. The most obvious gift is angular momentum. The Earth-Moon system rotates faster and carries more rotational energy than it would if Earth had never been struck. That angular momentum drives the tidal interactions that have shaped Earth's geological and biological history in ways we're still mapping. Tidal forces from the early, much closer moon would have generated significant tidal heating in Earth's interior, supplementing the radiogenic heat from decaying isotopes and contributing to the vigorous early tectonics that processed Earth's crust and drove the volatile cycling that eventually produced the atmosphere and oceans. The moon being close mattered. Tidal energy being high mattered. Theia's impact set the initial conditions for all of it. The second gift is more subtle and more contested: water. This is where I have to be honest with you about the uncertainty, because the origin of Earth's water is genuinely one of the most debated questions in planetary science right now, and anyone who tells you the answer is settled is oversimplifying. The leading hypothesis for decades was that Earth's water arrived late, delivered by water-rich asteroids from the outer solar system after the giant impact, because the heat of the impact would have vaporized any water present beforehand. That model still has significant support. But recent isotopic analyses of lunar samples, specifically hydrogen isotope ratios, complicate the picture. The moon's water, which exists primarily as ice in permanently shadowed polar craters, has a deuterium to hydrogen ratio that is statistically similar to Earth's oceans and to certain classes of carbonaceous meteorites. If Theia was compositionally similar to those meteorites, it may have carried water into the impact. Some of that water may have survived, or been partially reaccreted from the debris disk after the collision. The truth is probably a hybrid, some water from Theia, surviving the impact in hydrated minerals that later outgassed, combined with later delivery by asteroids and comets. The proportion from each source is unknown. But the possibility that some of the water in Earth's oceans, and therefore in every living cell on this planet, was originally carried by Theia is not a fringe hypothesis. It's actively being researched. The third gift is the one that gets least attention: Earth's large iron core, and what the giant impact may have done to differentiate it. During the impact, the iron cores of both Proto-Earth and Theia merged and sank toward the center of the combined body. This core merger, and the intense heat it generated, may have enhanced the magnetic dynamo that produces Earth's magnetic field. A magnetic field is not a luxury for a living planet. It is a shield. It deflects the solar wind that would otherwise strip away the upper atmosphere over geological time, the process that stripped Mars's atmosphere after its magnetic field weakened around 4 billion years ago. Mars lost its magnetic field. Mars lost most of its atmosphere. Mars lost its liquid water. These events are connected. Earth's strong, persistent magnetic field has kept our atmosphere intact for 4.5 billion years. Theia's iron, merged into Earth's core, is part of why that field exists at the strength it does. The fourth gift is the most philosophically loaded: time. The Moon's gravitational braking has slowed Earth's rotation from an early day of perhaps 5 to 6 hours down to the current 24 hours. This matters for life in ways that aren't immediately obvious. A faster rotating planet generates stronger Coriolis forces, more extreme atmospheric circulation, more violent and persistent storm systems. The early Earth, rotating much faster, had weather that would be unrecognizable to us, but life began anyway, in protected oceanic environments where surface weather was less immediately relevant. As rotation slowed over billions of years, surface conditions became progressively more stable, enabling the colonization of land environments and eventually the development of complex terrestrial ecosystems. The gradual slowing of Earth's day is a gift on a billion-year timeline. Theia didn't just create the Moon. It set the rotational clock. It deepened the core. It may have seeded the oceans. It stabilized the axis. Every one of these effects compounded over 4.5 billion years into the conditions that produced the biosphere we live in. The collision was not incidental to life on Earth. It was foundational. Here is the part that I find most difficult to sit with, and I want to take it slowly. If the conditions that produced Earth's habitability are as specific as the evidence suggests, a planet of a particular mass, at a particular orbital distance, struck by a particular impactor at a particular angle, resulting in a moon of a particular size stabilizing a particular axial tilt, then the question that follows is unavoidable. How common is this? In a universe of 2 trillion estimated galaxies, each containing hundreds of billions of stars, how many worlds have gone through a sequence of events sufficiently similar to produce something comparable to Earth? This is where the giant impact hypothesis intersects with one of the deepest unsolved problems in science, the Fermi paradox. Enrico Fermi's famous question, "Where is everybody?" rests on the assumption that if intelligent life can emerge once, it should emerge many times, and some fraction of those civilizations should have produced signals or artifacts detectable across interstellar distances by now. We have detected nothing convincing. The silence is strange. One proposed resolution is the rare Earth hypothesis, developed systematically by Peter Ward and Joe Kirschvink, among others. The core argument is that the conditions for complex life are not just uncommon but extraordinarily specific, and that simple microbial life may be widespread in the universe while complex multicellular life, and intelligent life, is vanishingly rare, possibly unique. The giant impact sits near the top of the list of requirements that the rare Earth hypothesis identifies as improbable and critical. You need a rocky planet in the habitable zone, not too difficult, these are now known to be common. You need plate tectonics to run a long-term carbon cycle, less common, and the conditions for plate tectonics are not fully understood. You need a large moon to stabilize axial tilt, rare, because large moons require large impacts, which require a very particular set of orbital circumstances. You need a strong magnetic field for atmospheric protection, dependent on core composition and rotation rate, both of which trace back to impact history. You need a Jupiter-like gas giant in the outer solar system to shield the inner planets from excessive comet bombardment, present in our system, absent in many others. Each of these factors is individually possible. The probability of all of them being present simultaneously, in the right combination, on the same planet, may be extraordinarily low. If the rare Earth hypothesis is even approximately correct, then the silence of the universe makes sense, not because life is absent elsewhere, but because the specific path to complex, technology-producing life requires a chain of cosmic coincidences that almost never fully assembles. We are, in that reading, the product of an improbable accident compounded by 4.5 billion years of improbable survival. And the moon above you tonight is the most visible evidence of how close the whole thing came to going differently. I want to be careful here not to overclaim, The rare Earth hypothesis is a hypothesis, not a settled conclusion. The discovery of even one example of independently evolved complex life elsewhere in the universe would substantially revise the probability estimates. The absence of detected signals doesn't prove absence of civilizations. Detection is hard, distances are vast, and we've been listening seriously for only a few decades. The universe is old enough that civilizations could have risen and fallen without overlapping with our detection window. The silence is data, but it's ambiguous data. What isn't ambiguous is this: we don't know how rare we are. We have exactly one data point, Earth. And everything we've learned about how Earth was made tells us that making it required things that could easily have gone wrong at a dozen different junctions. That should make us simultaneously humbled and alert. Humbled by contingency. Alert to the fragility of what contingency produced. The Sun is currently about halfway through its main sequence lifetime. It will continue burning hydrogen in its core for approximately another 5 billion years before expanding into a red giant and eventually engulfing the inner planets, including Earth. On that timescale, anything we can meaningfully call human civilization is a brief interlude near the beginning of the story, not the end. But within that vast remaining time, Earth faces challenges on shorter scales that are worth naming, not to induce despair but to complete the picture honestly. In roughly 1 billion years, the Sun's increasing luminosity will have raised enough to begin pushing Earth's surface temperatures toward the threshold of a runaway greenhouse effect, the same process that claimed Venus. The carbon silicate cycle, which has compensated for gradually increasing solar output over the last 4 billion years by slowly drawing down atmospheric CO2, will eventually hit a floor below which it cannot go. Complex surface life, dependent on liquid water and stable temperatures, will face pressures on billion-year timescales that are independent of anything we do. Plate tectonics will likely slow and eventually cease as Earth's interior cools further, removing the long-term carbon cycle regulation over timescales of perhaps 1.5 to 2 billion years. The Moon continues its recession at 3.8 centimeters per year, slowly weakening its stabilizing effect on axial tilt over very long time frames, though this becomes critical only on multi-billion-year scales. The Andromeda collision, roughly 4.5 billion years from now, will restructure galactic dynamics in ways that carry low but non-zero risks for the solar system. None of this is immediate. All of it is real. And knowing it doesn't change what matters in the present, it clarifies it. The world that Theia's collision built, that life spent 4 billion years adapting to, that we have the extraordinary privilege of existing within, is not permanent on cosmic timescales. It never was. The question has never been whether it will last forever. The question is what we do with it while it's here, and how carefully we tend the conditions that make it livable on the timescales that actually matter to us. If the rock that became the Moon had arrived at a slightly different angle, we would not be here to ask the question. We are here because, 4.5 billion years ago, something went right in the most catastrophic possible way. That is the story of Earth. And every time you look up at the Moon, you're looking at the proof. There is a particular kind of knowledge that doesn't make you feel powerful, it makes you feel small in the best possible way. Not the smallness of insignificance, but the smallness of someone who has just understood the true dimensions of something they thought they already knew. You came into this documentary with the Moon. You leave it knowing that the Moon is a scar, a memorial, and a life support system all at once, the crystallized remnant of a catastrophe that happened to be exactly the catastrophe we needed. Theia is gone. Or rather, Theia is everywhere. In the iron at Earth's core. In the silicates threading through the mantle. In the isotopic ratios of oxygen locked inside every rock geologists have ever sampled. In the tilt that gives us seasons, in the tides that drove early chemistry toward complexity, in the magnetic field that kept our atmosphere from being stripped away by solar wind before life had a chance to get started. You cannot point to Theia because there is nowhere to point that Theia is not. That is what it means to be fully absorbed into another world. I'll admit something, when I first went deep into the giant impact hypothesis while putting this together, my instinct was to treat it as a solved problem, one of those science stories where the mystery has already been wrapped up neatly and the job is just to explain the answer. That instinct was wrong. The more I read, the more I found genuine uncertainty underneath the confident surface. We don't know Theia's exact size. We don't know whether it hit at a low angle or a steep one, and the distinction matters enormously for the Moon's composition. We don't know whether 2 or 3 or 4 similar near-Earth co-orbital bodies existed in Theia's neighborhood before the late heavy bombardment reshuffled everything. The giant impact hypothesis is the best explanation we have. It fits the evidence better than anything else proposed, but fitting the evidence better than alternatives is not the same as being completely understood. Science is honest about that gap in a way that I think deserves acknowledgement. What we do know is this: the solar system of 4.5 billion years ago was not the orderly, stable structure it appears to be today. It was a construction zone undergoing violent reorganization, and the worlds we see now are the survivors of a selection process that was brutally indifferent to any individual outcome. Earth survived and became what it is partly through processes we understand and partly through contingencies we are still mapping. The Moon exists because of a collision that, by any reasonable probability assessment, had no obligation to produce something so geometrically and chemically suited to stabilizing complex life. And yet here we both are, planet and moon, locked in a gravitational conversation that began with a planetary catastrophe and has continued without interruption for longer than the mind can honestly hold. The next time the moon is full and you find yourself outside in the dark, standing still for a moment, I want you to hold 2 things in your mind simultaneously. The first is the sheer age of what you're looking at, a surface that has changed very little in 3 billion years, older than any continent on Earth, older than almost any structure our own planet still carries visibly. The second is the violence of its origin, the fact that the light reaching your eyes is reflecting off material that was once molten, that was once part of a debris ring, that was once part of 2 separate planetary bodies moving toward each other across an emptiness that no longer exists. Both of those things are true at the same time. The stillness and the violence. The permanence and the origin in chaos. That is the universe as it actually is. Not a backdrop. Not a stage. A process, ongoing, indifferent, occasionally catastrophic, and somehow, against considerable odds, productive of the very consciousness now standing in the dark looking up and wondering where it all came from. And if that question keeps you up tonight, good. It means you've been paying attention to the right things.